So welcome all of you. So this one is the sixth session, sixth problem solving session of the course Structure, Stereochemistry and Reactivity of Organic Compounds and Intermediate, a problem solving approach. This course, uh, firstly I will introduce myself. I am Vijay Rahane, Prime Minister Research Fellow at the uh, IIT Delhi and the University of Queensland Joint PhD program. This course is taught by Professor Amit Basar from the IIT Kharagpur on a SWAYAM and NPTEL portal. So I will solve here some problems based on the topics which are covered by the professor on the NPTEL in the week 6. Right. So here is the first problem. The first question is among the following radicals shown, the radicals show pyramidal geometry is. So they have given some, example of the radicals like a CF3 radical here, 3 radical. Second one is the CH2. I will just draw here by splitting the structure. Hydrogen here, hydrogen here, C double bond O, CH2, CH3, right? Third one is the pH, which refers to the benzene ring, and here CH2 means carbon, and here hydrogen, right? So here is one radical and pH radical. This pH radical will be, this radical lie in the low, which is in the plane of the benzene ring and the perpendicular to the 5 orbitals, right? So when the benzene ring, I will just, for sake of understanding, I will draw it like this. See, if the benzene ring is in a plane, the radical also lie in the same plane, which is of the benzene ring, and other pi orbital, which is perpendicular to this plane of benzene ring, right? So this pi electron cloud will be above and below of this benzene ring, right? So here we'll neglect one by one possibility. So we'll first look at this pi orbital, radical of this phenyl radical. So if you see, this is a planar one geometry. So this one is the planar, not pyramidal. So this option is neglected. Second option, if you see here, this one is the pH CH2 radical, right? Here is the radical, and if you see here in the this ring, this radical pH CH2 radical, this radical gets stabilized because of this resonance. I will just draw, add one slide. So right. So first here we will see radical. This radical, if you see the resonating structure, in this resonating structure, the electron will localize in this fashion. So CH2, the radical will go to here, here, and here. So overall, this and it again resonate in the entire plane. So one way electron will be here, right? So again, it is getting resonated in the ring. So the radical goes to here, and the double bond position of the double bond will get rearranged. So this one is the radical getting formed. So if you see this radical, this one is also a planar radical, not a pyramidal, right? So here, this option is neglected. This one is also a planar, and this CH2 C double bond ET. We'll draw the how this CH2 C double bond O ET, this radical. If you look at this radical also has the stabilization in this fashion. So the CH2 O radical and O ethyl, right? Ethyl will be, I will draw in this fashion. You can also write in the in this way. So this one is the radical. It, uh, this one will be a stabilization. So if you see the structure of this ethyl radical also, so this one also not a pyramidal geometry, and so this option is also neglected. This one is a pyramidal. But if you look at the CF3 radical, so I will explain the CF3 radical in the slide. So this CF3 radical. So this CF3 radical has a special. This one is a pyramidal geometry. I will explain here because the fluorine is very fluorine has very high electronegativity. Right. If you see the electronegativity, the fluorine has the highest electronegativity, right, in the periodic table. So because of this, uh, it prefers to be so it has the yes character. It I prefer to the in the form of sp3 hybridization. The CF3 will be preferred to stay in the sp3 hybridization. In this one, the 25% of yes character is present. And if we see the fluorine, the lone pair of electron on the fluorine, although it has the lone pair of electron, right? So three lone pair of electron are present on each fluorine atom, which is not able to resonate in the to stabilize this radical, right? Because of this electronegativity of the fluorine. So it is not possible in case of uh, this CF3 one. And also the lone pair repulsion. If you see this radical and the lone pair present on the fluorine atom, they repel each other. So because to stabilize the structure, what happened? The fluorine, the CH3 radical, which here there will be a repulsion. So so the repulsions happen between this lone pair and the this radical and the electron pair on the fluorine atom. So that's why this fluorine atom is it try to stay in the a pyramidal form. So this is why the CF3 is the in the form of pyramidal has the pyramidal geometry. All other phenyl radical has planar. Benzyl radical has the also a planar geometry, and CH2 CO2 ET. This radical due to conjugation, this CH2 as seen here, it involved in the conjugation, so it has the geometry like this. So this one is the correct option. We'll see the next question. In the next question, what they have mentioned, the correct order of stability of these following radicals. So they have given three radicals. We need to just show the order of stability. So I will draw the structure. So this one is the structure of this radical. If you see this radical, the lone pair like this, the stabilization is possible in this case, and from both sides. So this is how the radical gets stabilized in this first structure. In the second structure, what is getting happen? O CH3 radical. So in the second case, what happened? The lone pair of electron helps to stabilize this radical, right? So the lone pair of electron present on this. So this radical is getting stabilized in this one radical. And in this third case, this CH3, this hydrogen atom, they are electropositive. So it helps the bond pair of electrons present on the bond, which is just has got the polarization towards this carbon. So this got some stabilization. So if you compare this all these three radical, which is the most stable radical? The second one is the most stable radical, because most stable as compared to this table, as compared to this one other two radical. So the order will be the second radical will be a more stable, and then if you compare 1 and 3, then this has only due to stabilization due to only some polarization. But if you compare here, this one structure is possible. Another structure is the if it involve in the delocalization to this side, right? So another possible structure will be OET. Or so these two possible structure, resonance structure are possible for this structure one. So this is why the structure one is stable as compared to this methyl radical. So the order will be the second, first, and the third. So the correct option will be a B option, in which the second radical is more stable than first, and first radical more stable than the third one. So we'll see the next question. So next question is, which pair of reactant is expected to give a highest yield of monomeric adduct? So they have given three reaction, 1, 2, 3, and we need to answer. Reaction condition is same. We need to select which pair of reactant is expected to give highest yield of monomeric adduct. So if you see this polarization in these structures, the polarization in this one, first one will be lone pair of electron will be, it is not here, and here will be. So the delta positive charge will be lie. So I will just take, I'll write here only. So yummy. In this one, the lone pair of electron on it doesn't resonate like this. So delta positive will be here, and here will be a delta negative charge, right? So this center is electropositive, this center is electronegative. So this second both are same. In this one, what happened? So the polarization is getting reversed because of this electron withdrawing cyanide group. In this one, the direction of the localized this bond pair will be from the double bond to the group of this cyano group. So the position electropositive will be here charge and electronegative charge will be here, right? Wait a minute, I'll just. So in this one, if you see in this one, the localization will be like this, and this last option, this reactant, it has the cyano group. Both are equivalent. So in this one, there will be a no polarization, such polarization. So obviously, this fourth, there are many possibility for to get reacted this reactant. So it can be reacted at this position, this carbon atom or this carbon atom. But both, if you see these both sides are equivalent, right? One, two, one, two. Both sides are equivalent. So when the radical attack at here, when the radical attack here or radical attack here, the both this reaction gives the same product. So the form product is exclusively a single. And if you solve one by one, this by this one. So in the first one, what will be happen in the first reaction? This CH2 C double bond O ET. This one is the electrophilic. This radical is electrophilic radical, and when reacted with this O ME, this one is the nucleophilic alkene, right? So what happened when this bond react here, react, it will be shifted to like this, and this side will be a ME, right? And the reaction of this at the center will be this forms this radical, right? So this one is the like this delocalization is possible for this one. So when these two get reacted, so this side, so this is how they get reacted, right? So this form a compound containing Me, right? And which, so this get resonance stabilization. So here will be a Me O plus C O 80. See, this one is the captative stabilization, right? So this is why this A mechanism, if you compare this A mechanism, this gives the highest yield of the monomeric product. In the next question, is consider the following statement and identify correct statement. So they have given here example, first phenyl radical, then benzyl radical. This one is the allyl radical. This is one is a tertiary radical, that is methyl groups are adjacent to this carbon atom which containing a radical. And first statement is the 1 and 2 are pi radical, whereas 3 and 4 are sigma radical. So we need to understand in this all the four, which is pi radical and which is sigma radical. First, we need to distinguish all other. Since the first one is a phenyl, and if you see the lone pair, the radical on this phenyl ring, which is at the sp2 carbon atom. sp2 hybrid at sp2 hybrid orbital, right? In this second one, this carbon, this radical, this one lie in the p orbital, right? In the third one, this radical again on sp2 hybrid orbital. And this methyl one, you see this one. So this radical, this on the carbon atom which containing a p orbital. So clearly you can neglect the option. Only 2 and 4 have these two, right? This 2 and 4 unpaired electron radicals and hybrid p orbital. So they are pi orbital. This 2 and 4. So the option B is the correct one. 2 and 4. Where they have given 2 and 4 are the pi radical. Yeah, right. Here they have given 2 and 4 are the pi radical, whereas 1 and 3 are sigma radical. Because if you see this one, it clearly lie in the sp2 hybrid orbital. And here also 1 and 3, these are the sigma. This one is the pi. So this one is a simple question. We just need to understand. Firstly, we'll draw the structure, and then we'll assign this low radical, which is on which orbital. So here in the phenyl radical, it is this radical in the sp2 hybridized on the sp2 hybridized orbital. In this one, benzyl one, the radical is on the carbon atom, right? The unpaired electron is belong to the p orbital of this carbon. So this one is the pi radical. In this vinylic radical, if you see here, this radical also, if you see, it be on the sigma radical, that is sp2 on the sp2 hybridized orbital, right? So this one is the sigma radical. And again, this tertiary radical is the pi orbital, p orbital, belong to the carbon atom. So and the unpaired electron is from the orbital of the carbon atom, right? P orbital of the carbon atom. So this is how such question we can solve. We can assign a radical where it belongs to. If there is another example, suppose is there in OMe, right? And if the radical will be here, then this radical also, if you see such radicals is present, then this radical is also a sigma radical, right? And any kind of radical like this one, secondary radical, if you see, if it is lie away from, so I'll write this in the next page, so it will not get more congested. So if the radical present here, this one belong to the similar example here like this, right? The sigma one. Correct. This one is the sigma phenyl orbital. If you see the phenyl radical and present, this radical is in the perpendicular plane, right? So this one is the sigma radical. So like this, we can solve such questions. We'll take a next question here now. So this one is the fifth question, and here what they have given: identify the major product A formed in the following reaction. They have given a reaction sequence, and we have to solve this reaction. First, they have given a compound. I will just split here groups so as we can find out which is the exact reaction site, right? So if you see here NH, so we'll start here from here. N, it contains one hydrogen attached. So this one system, it has the one CO2 BN group, right? So we'll, for sake of understanding, we'll split the group so as we can able to find out the active site in this reaction. So in this one, the first reagent they have given, and we need to perform a reaction on this. So if the reaction goes on, hello, can you please mute yourself?
Hello.
Yes.
Hello, sir.
Yes, please, you can ask.
Sorry. Hello. Am I audible?
Yes, you can. You are audible.
Okay. No, you were saying something.
Do you want to ask a question or?
Hello.
Yes, Amruta, you can ask.
Good evening, sir. Actually, I'm not a student. I'm NPTEL employee, sir. I'm here to monitor this session.
Oh, thank you. I will just stop some recording.
And
So I have just draw a structure. So I will just split these structures so as can able to understand which is the reactive site here, right? So in this one, the reactive site will be. So when the reaction happen, the O negative charge in presence of DCC. We know the DCC is a coupling reagent help to couple this such species. So the OH will attack on this center, right? So this OH I will draw here. This OH will attack here, and this the form product will be like this. Like this product is getting formed in this one, right? In the first step, and in the second step, what happened when it reacted with this CbR Cl3 in presence of light. So I will draw the structure in the next one. So when it reacted with this Br Cl3 in presence in the light, what happened in presence of light? This it formed a radical species, and this radical species gives rise to a Br radical and C. Just draw here CCl. Oh, sorry, CCl3 radical. So this radical, these two radical are getting formed, and when the this Br radical now stay in the reaction, and if you see here, this CCl3 radical, what happened here? This decarbonylation happened. So here, if you see the reaction mechanism, this goes to here, and right. So here at the end, it goes to here, and this goes to here. So these radical are getting, and again, right. So this S and this CF3 radical get reacted. So the what product will be formed? Here will be a CH2 radical, right? CH2 radical plus here one there is CO2, and here if you see this nitrogen and sulfur C Cl3, and since this involved in here in the remaining one radical will come here, right? So here will be a double bond like this. These three product will be getting formed. So this one is the product in this reaction. So we'll choose it from the options they have given. So in this option, we can see which one is the correct option. So we see. So this one at the end, what happened is then this Br radical, and this CH2 radical get form a bond and form a so the which is correct option in this one, right? So this D is the correct option. Here no Cl because this if you see the radical formation CF3 and Br. So like this cleavage is more feasible instead of Cl, Cbr, Cl2. So this one is the preferred one because the bond dissociation energy for Cbr bond is less as compared to CCl bond. So CCl bond is more stable as compared to Cbr bond, and hence in presence of light, this Br radical is formed, and CCl3 radical, these two radicals are getting formed. This is because if you see the sp2 overlap, sp2 sp3 overlap, sp2 overlap is more stable overlap, right? So in such cleavage, this sp2, in between the chlorine and carbon atom, this sp2 overlap present. So this one is the stable bond as compared to cbr1. So this option is the incorrect one. In this one, if you see this one carbon atom is less, and in this one, what happened? One carbon atom is more. 1, 2, 3, 1, 2. Here should be a cleavage, and so 1, 2, 2 carbon should be there. Here, one carbon is more. So we can directly tick the option D. D option is the correct option in this one. So the next question, we'll solve the next question. In this next question, what they have given, the major product X and Y in the following reaction are. So they have given two reactions, and we need to give the which is major product. So first we'll solve first one, which is X. So MEBr. When it reacted with BU3SNH, so we'll draw the reaction mechanism. BU3SNH and AIBN. What they have given? They give the BU3SN radical and hydrogen radical, right? We all know the this AIBN help to form a radical from this BU3SNH, and then when this BU3SNH, this one first one, in the second step, what happened? This BU3SN plus MEBr. So like this radical initiation will happen, and it forms a BU3SN Br bond, and plus methyl radical is getting formed. And when such step twice, this methyl radical will further converted into the, when it reacted with this one methyl. So here if you see, it can attack, this methyl radical can attack here or can attack here, right? So which is stable? So after attacking here at the both places, so in one, if the attack takes place at this A path, then the radical will be goes to here, right? And if attack takes place via this B path, the radical will be here. So the secondary radical is more stable. So attack A is more feasible. So what happened? The product will be a CH3. This secondary radical is getting formed, and again this H radical already, which is eliminated here, will be then in the CH3, CH2, CH2, CH3. So the A product will be, X product will be this one. So these two are the product. If the attack takes place at this position, the radical will be at the terminal part. So the primary radical is unstable. Secondary radical is more stable as compared to primary radical. So the attack A is more feasible. Right. So that's why the attack, the A path will be getting followed. So X will be this one. So these two options are incorrect. And in the second one, I will take it in the next slide. So here we have already solved. This one is the correct option. This one is the correct. X is correct. These two are wrong. Now we'll solve this second path. In the second path, the similarly, as we have seen, Bu3 SN H plus AIBN, they give the BO3 SN radical plus hydrogen radical, and when it react when BO3 SNH reacted with methyl bromide, right? When it reacted with the MEPR, I'll draw a little step by step so as you can able to understand. This one is the first step. In the second step, on CH3 Br plus BU3 radical, it form a CH3 radical plus BU3 SN-Br, right? This methyl radical, then what happened? This CH3 radical is then reacted with this molecule, right? Yep. Now here we can see this CH3 radical can attack at this position or can attack this position. So there are two possible pathway, this A path and the B path. So if the radical follow this path, if the reaction mechanism follow this path, A path, then radical will be at this position, right? And the radical which is adjacent to this CF radical is less stable because two fluorine atoms are attached here, right? So these two fluorine atom make this radical unstable. So which radical unstable? Of the methyl fluorine will be here, CH3. If A path is getting followed, then here will be a radical which has the two fluorine atom. This is unstable, right? And if attack will take on by the B route, right? So then what happened? This fluorine will be here, hydrogen will be here, C F2 CH3. So this one is product getting formed, and the radical to which only one fluorine atom is attached. So this one is the stable. So after attacking this hydrogen radical, so the product form which contain here hydrogen. So which option is correct here? So this one is not possible. So methyl should be at the side of 2 fluorine. So which is in this option? Already seen these two are option are wrong. In this one, methyl should be side of 2 fluorine. Here, see, here methyl 2 fluorine. Here methyl is at site of 1 fluorine. So this product give rise to methyl at 1 fluorine. So this one is the incorrect. So option C is the correct option, right? So you just need to understand stability of this radical. So in the intermediate, in this step, the radical form this. If follow A path, then this radical is formed. If follow B path, so this radical is preferred and more stable, and that's why the corresponding product will be the major product. So this C is the correct option. So we'll take a next question. The question 7. Question 7. Identify the major product N in the following reaction. So they have given a starting which contain a hydroxy group, chlorine as well as OAC, and reacted with the PbOAC4. So which is major product form in this reaction? They have given 4 options. So we need to go a step-by-step mechanism, right? So to understand the mechanism, we need to first draw this compound in a chair form, right? So if you draw the chair, if you see here, this one is the anti, and this methyl is above, right? This chlorine will be below. OAC above, right? Like beta, and So this is how the structure of this, and it has the chlorine which is down and hydroxy group which is above, right? So when it reacted with the PbOAC4, what happened? This OAC, I will draw the split. I will split the structure PbOAC. When this coordinated oxygen coordinated with this one, the OAC get eliminated. So what happened? Minus ACOH takes place, right? And Pb coordinated with this at this site from site of oxygen. So the in this intermediate is CH2H. Here will be a O, Pb, OAC thrice, right? Since one ACOH is getting cleaved in this one, minus ACOH. So in this one, what happened? This Pb is getting coordinated from the site of OH. So OH, since OH is at the above side, so in this one, the radical is getting from this hydrogen at the methyl is easy to pick up by this Pb. So what happened in the next step? I will draw the intermediate again here. O and this CH2 radical is getting formed in this one, right? And OH again come back. So next, this OH, lone pair of OH help to form a bond between this CH2 carbon and the oxygen bond getting formed, and the intermediate form will be then will be like this. So in this one, so the newly formed bond will be this CH2. Here will be O, and this bond is getting formed between this carbon and oxygen. We'll erase these hydrogens. So this bond is getting formed. This is newly formed bond, and here will be two hydrogens. So this one is the product, right? It has the one chlorine here. Sorry, I have forgotten here chlorine in all places. So this one is the product. So we'll compare which is the correct option. So in this one, the chlorine downside CH2O. So no, not epoxide. Here they have given. So the C option is the correct option. So like this, we can solve many questions based on. We just need to understand the geometry, stereochemistry. Because if you see here, which the palladium Pb is coordinated with this hydroxy group, and then the radical form on the methyl group. If the methyl group is and the hydroxy group are not synced to each other, then this product will not form, right? So the correct option is the C. Next question is the identify the product P and Q for the following reaction. They are given two reactions, P and Q, and we need to solve. Identify P and Q in the following reaction. So we will take, they are given options. Right. So this is the reaction. We'll solve the, we'll go through a step-by-step mechanism and then comes to which option is the correct among this A, B, C, D. They are again the 4 options. So we need to limit one by one option and get to a correct option. So here the mechanism will be, if you see here, pH S S pH, right? So in terms of AIBN, what happened? So pH S radical are getting formed, and since this homolytic cleavage will help happen, so two such radicals are getting formed, right? Two radicals are formed. Then this radical, it reacted with this alkene. The two alkenes are present, and it reacted with this reactive alkene, right? So this was reactive alkene because it has a polarization. I will draw here. Right. So when this PHS radical reacted with this alkene, it forms a bond in this fashion, and this one electron shifted here, right? So another one electron, since this is 3-member ring, so it is prone to open. So here the red form, it forms a radical, right? So what the product will form is pH S on this carbon atom, contain one carbon. So here will be a double bond. O. Sorry, this here pH, right? So this one is the product formed in this one, in the first step, and again it reacted with this radical. Since here radical is formed, because of this oxygen, it got some stabilization. So it involved like this, and right. So minus pH double bond O pH, right? So this one will be getting eliminated in this, and the product will be here. I'll draw it with different color so as you can able to understand. So here will be one radical then, right? So pH C double bond O, pH will be removed, and the formed product will be pH S, right? Here will be double bond and CH2 radical. This product is getting formed in this step. So when this product, I will just copy this product to the next slide. Right. Reacted with this second, this compound, TBU, right? OTBU. So when these two getting reacted, so if you see the polarization here, O radical. So the product will be and which is then converted into this is just a reaction. So the stoichiometry of this bond will not be defined because it's radical mechanism, and here there will be a double bond. So like this will be a product. So here the P and Q will be here P, this one, right? This we have seen, this one product, and this one is eliminated in the reaction mechanism. So this one here already right. This one is the one product, and another product will be this one. So these two products are getting formed in this the reaction. So next, so option in this one, option B is the correct option. Next question is the identify the major product M in the following reaction. So they have given a reaction in this one, SMI2 THF at room temperature, and SMI2 generates a radical at carbonyl center. They have given hint also. So in this one, what happened? This C6H13 double bond O CH3. When it reacted with the SMI2, it formed a radical at carbonyl center, right? So like this, and this reacted with this radical attack on SM. So the product will be C6H13 O SMI2. Excuse me. So this one will be, this radical is getting formed because of this SMI2 reagent, and when it reacted with this alkene, right? This radical reacted with this alkene. So how it will be react? It forms a C6H13, right? Here O SMI2, and here will be a this radical attack at this center, right? So it will go here, and C radical will be formed. One methyl will be CH3 here, and one carbon, two carbon. Third one is the carbonyl, right? So this one is getting formed, and in the next step, what happened? I'll just draw it neatly so as you can understand. So in this step, what happened? The product will be C6H13. It has OSMI2, one methyl group here, and then when you attack it at this position, so one carbon, this 1 2 3 carbon, 1 2 3 carbon, right? So when you attack here, this bond goes to here, right? So here it will be a bond with O radical and O ET, right? So this one is the product in this first step, and then this intermediate is getting converted into so this one is the product. So it's intramolecular cyclization takes place and removal of OET group will be getting kicked out, right? So this one will be a product in this reaction. The next question, so correct option here will tick. So this D is the correct option. In the next question, they have given identify the major product E formed in the following reaction. So here they have given a reaction in which the major product, which is major product. So here they have given BU3SNH. BU3SNH helps to in terms of AIVN, it forms a radical. So we will draw a reaction mechanism for this reaction. The reaction mechanism for this one is the so BU3SNH plus AIBN. It forms a plus hydrogen radical, and when this BU3SNH radical, BU3SN radical reacted with this or starting right. This radical we attack here, right? So one bond shifted here and here. This O radical is getting formed in this step. So the product will be like this. So this one will be O radical, right? Here they are carbons are beta. So here also it will the stereochemistry remains same because only one bond getting cleaved, so another bond is intact. OBN and SnBu3, right? So in this step, what happened? 1,3 hydrogen shift takes place, right? Because it has 1, 2, 3 here. There is a hydrogen. So this hydrogen, uh, it forms a it. So 1, 3 hydrogen shift. So it forms a SN. Sorry, I have missed here. So oxygen at this carbon, right? So here will be a radical. and then it gets cyclized because this CH2, this bond again getting fluid. So like this, and it did form a bond with at this position, but remain always check here when this group is at lower side, right? So if you draw the stereochemistry here, so this group will be lower from bottom side. So it attack from bottom side, and this hydrogen present will be comes upside down after attack. So the stereochemistry of hydroxy group will be beta, and this hydrogen at the center also a beta. Here will be a double bond, this CH2, and this 1, 2, 3, 4, 5. This 5-member ring is getting formed in this step, and it contains a OBN group, which is at the 1, 2, 3. So here, the stereochemistry of the BN group will be undefined, but the stereochemistry of these hydrogens will be obviously a beta, hydroxy also a beta. So this one is the product formed in this reaction. So if you see the correct option, so in this one, 1, 2, 5-member ring. So here no, in this one you need to compare which is the correct product. So if you see this OBN with attack here, right? So hydroxy and OBN should be apart from each other. So this A option is the correct option. So if you compare these options with our product, this one is the product. So which option is correct match? This A is the correct match. So the option A is the correct option. So this is how we can solve questions of this such type on radical, where the radical is stabilized, and reactivity of radical in the progress of reaction mechanism, and based on how the stability of the radical helps to direct a reaction mechanism. So this all about the today's problems. So I will just stop here, share, and pause recording. If you have any question, please ask. Forum is open for question and answer. We'll just stop